Okay students, so this is part 2 of optimal input combination. Now you people know what is isoquant and what is isocost line. This is isoquant and this is isocost line. On every point of isoquant, your total output is same. On every point of isocost line, your total expenses for production is same. Here you are hiring labor and capital in different ratios, and here labor and capital you are taking, and their different combinations you are using on isoquant. So where will be the optimal input combination? I mean to say, by using labor and capital in different ratios, you can produce same output, suppose 100 units. So which combination you should select out of these combination? That will be optimal input combination. And what is optimal input combination? Or you can say least cost combination. That combination which provide you 100 units of total production with minimum cost. So you have to find out that particular combination. Here, if this is your isoquant, we have to draw a tangent which is having slope like this line. In fact, we are going to draw isocost line here in such a way that it is tangent to your isoquant. So here I have drawn this line. So this is isocost line and this is isoquant, and this is the point. Suppose this is point P. On point P, both curves are tangent, or you can say touching each other. They are not cutting, they are only touching each other. So this is the combination we should hire to produce 100 units. And why this combination? Because this is available on least cost or minimum cost. If we compare this P point with any other point, suppose here is the point and suppose this is N point, suppose. So on this point, production is 100. On P also production is 100. But what about cost of production on N? So suppose we are drawing this isocost line here from N point. Obviously your total expenditure will be higher on a higher isocost line. So that's why other than this point P, all the points are giving us equal production but at a higher cost. So this is the point which is showing us this combination of labor and capital, which is least cost combination to produce 100 units. So here will be our equilibrium. I mean to say equilibrium of the producer. If generally we talk about decision making by a producer, suppose you are a producer and you have to produce some commodities by hiring labor and capital. So you will focus on two things. One is productivity of these inputs, and second thing is cost of these inputs or factors of production. So productivity is exhibited by your isoquant and cost is exhibited by your isocost line. So all important things are combined here on this point, because if we talk about slope of isoquant, it is directly related to the productivity of labor and capital, because we are substituting our capital with labor if we are moving like this on this isoquant, and obviously this substitution will be depending upon some rate, and that rate is directly related to their marginal productivity. I mean to say marginal productivity of labor and capital. So this is our least cost combination. Now, we can explain production in long run as well as in short run with the help of these curves. How we can explain? First of all, I am explaining you increasing returns to scale. This is our isoquant for production of 100 commodities. Let me draw a straight line. It will help me to draw the diagram clear. So to produce 100 units, you are using this much of labor and capital. Labor and capital. Now we will increase our production by 100 units. So I have increased our production. Now 200 units are shown by this higher isoquant. But if you compare labor used for next 100 units, you can compare. Earlier we were using this much of labor to produce 100 units, but now lesser number of labor we are using to produce next 100 units. Again, if we want to produce more products, suppose again by 100 units I am increasing my production, and if you compare with previous situation, now for producing next 100 units even we need lesser of a labor than the previous situation. Suppose in the starting 10 laborers were required to produce 100 units, but for next 100 units you can compare, this is less than this amount. Suppose you need only 8 labor, and for next 100 units you are using suppose 6 labor. Same is happening to capital also. If you can see, same thing is happening here also. This difference is decreasing. So why it is happening? Because I am drawing this diagram in such a way that this difference between these isoquants, this difference between isoquant is decreasing. You can see here. So if you are drawing your isoquants like this, means their gap is decreasing, their distance is decreasing. This is example of law of increasing returns to scale, because every time to produce more you need lesser inputs. So this is example of increasing returns to scale. And how to show decreasing returns to scale? Simply you have to draw isoquants in such a way that their difference is increasing. So to draw the diagram clearly, I always take help of a straight line. Even without this straight line you can draw, it is up to you, but I feel more confident when I draw this straight line. For 100 units, this is our isoquant. See this distance. Next distance should be increased again. Okay, so if these are your isoquants, you can see, okay, we are increasing our output by 100 units every time. So now you can compare. Earlier only this much of labor was required to produce 100 units, but for next 100 units more labor is required, and same is happening for next 100 units. So every time increase in our output is 100, but every time increase in our input, I mean use of our input, is increasing. To show constant returns to scale, we will draw this diagram in such a way that all the isoquants are on equal distance. Hundred units, 200, 300 and 400. So every time you are increasing your output by 100 units, and input requirement is same for every 100 units. So this is example of constant returns to scale. Constant returns to scale is production in long run. If you want to draw these three situations without using that straight line, you can draw it like this. If this distance is decreasing, this is example of increasing returns to scale. If distance is increasing like this, this is example of decreasing returns to scale. And if distance is equal, this is example of constant returns to scale. Let me tell you, we are using labor and capital inputs here. So in this way, we can use these tools, isoquant and isocost, to show production in long run and as well as in short run. Now, we will talk about expansion path. What is expansion path? You can say that expansion path is a line which is joining all the optimal input combinations for producing different level of output. I mean to say, this is your isoquant and this is your isocost line for producing 100 units. And if this is your isoquant and isocost line to produce 200 units, if I join these lines, this line is called expansion path. What is meaning of expansion path? If in your production unit, if you are increasing your production, so every time to increase your production, what combination of labor and capital you are using, that combinations are joined by this line. Again, if you want to increase your production by 100 units, then this is isoquant for 300 units and this is isocost line to produce 300 units. So you can join this line. So this is called expansion path. This is called expansion path. Okay, next now we will talk about ridge lines. What is meaning of ridge lines? Let me explain what are ridge lines. If this is our isoquant, I always draw this part of isoquant, but if we draw further next part of this isoquant, now see the darker area. What is happening on this area and on that area? Suppose this isoquant is to produce 100 units. So this much of labor and this much of capital we are using to produce 100 units. But if we increase our use of labor from this point to this point, you will see that we are using same capital but more labor, but still our production is 100 units. So here 2 capital and 10 labor we were using. So here 2 capital and 10 labor we were using. Here 2 capital and suppose 12 labor we are using, but still our total production is same. Why it is so? Because these 2 units of labor which we increased here could not add anything in your total production. It means marginal productivity of these labors are 0. So we will not deal with that portion of our isoquant. Similarly, if you compare situation here with this much of capital and this much of labor. Now, with the same labor, we are using suppose more capital. You can see we are using more capital, but with same labor. Again, production is 100 units on this point also and on this point also. It means this additional capital which we are using is not adding anything to your total production. So it means marginal productivity of capital became 0 here. So that's why we will not deal with that portion of isoquant. So we will not use that portion of isoquant and this portion of isoquant. So these are 2 points, and between these 2 points, this portion of isoquant we will be using for our analysis. Similarly, for higher level of production, again there will be these 2 points to produce 200 units. So these points, if I join these points and these points, these are called ridge lines. This is lower ridge line and this is upper ridge line. So ridge lines are those lines which are joining that point of isoquants where marginal productivity of one factor becomes 0. So these are called ridge lines. Next, what is difference between short run and long run production? In short run production analysis, we have to keep at least one input constant. So if we are using one input as a constant amount, then can we explain production in short run with the help of isoquant? Yes, we can. How? See here. If these are isoquants, roughly I am drawing these like this. Okay, labor and capital we are using. If we fix our capital, we have fixed our capital, only we can increase our labor. So in this way we are operating on these combinations. So we are increasing use of our labor with constant capital. In this way we can explain our production in short run with the help of isoquants. These are our isoquants. Again, if we see the difference between these isoquant, we can explain production in short run. I mean to say 3 situations in the short run, like increasing returns to variable input, decreasing returns to variable input, and constant returns to variable input. How? Again, difference between these isoquant we will be using here. If this difference is decreasing, this is case of law of increasing returns. If this difference is increasing like this is example of decreasing returns to variable input, or you can say law of decreasing returns. And if this distance is equal, so every time to increase 100 units, we are increasing labor in same amount. This is same amount, so it in this way. So this is equal. Here this distance is increasing and this distance is decreasing. So in this way, with the help of isoquant, we can explain our production in short run also.